It feels I was here just yesterday. So, yeah, exactly. So, we're going to do a network talk this time. Hopefully it's better. This talk right now, I told you I ran my own autonomous system yesterday. We're going to talk about it today. And this is currently applied and working in my environment, and it is serving some traffic. But I'm adding a few extra nodes into the mix so it can I can get the point across a little bit better. So in this presentation, we start with a network, and you have to build a network, of course, but that's out of scope here. In this network, you can have multiple locations, and then you can have transit and peering sessions, and then you also need a backbone to interconnect all of these data centers. And in these data centers, I have some servers. I have some compute capacity with CPU cores, memory, SSDs, anything I need. And the reason for that is that you have to run important applications there. All these enterprise corporate things. And what I use to manage all of these applications is Kubernetes. So it's basically I have created a cluster across all servers that I'm using, and they can be automatically managed. And the reason I used Kubernetes is because I want Antonis, the network engineer, to not have to talk too much to Antonis, the developer, and not too much to the Antonis, the sysadmin, and try to abstract away a few concepts. So when I'm writing code, I want to focus just on writing that code. I want to deploy this code now. I can say run it anywhere. I don't care. I don't need to have to create virtual machines. I don't need to have to do any of that, get IP addresses. Just get this thing and run it anywhere you have capacity. And then it's up to Antonis, the data center guy, to buy new servers and install them and add additional capacity when it is needed. So this simplifies things for me, even if it's just a single-person operation, let alone in a company. There are some benefits to be had. And now for some of the applications that you're going to run, you want them to be exposed to the internet. So if you have a web server or a DNS server, clients from outside your network, they have to come and they have to get a response back to all of their requests. Not all applications are exposed, like some of them can be internally available only, but you will have that need to expose applications to the outside. And if we have like a 3-node cluster in this example, you just tell Kubernetes, I want to run 2 web servers, one for redundancy and another one to serve my traffic. It's going to say, okay, I'm going to run one in Switzerland, I'm going to run another one in Frankfurt, and that's it. And all these servers, they have different IP addresses, like they belong to a different LAN network. You shouldn't stretch like LAN networks across Europe. So now we have the thing that all the websites we run, what are their DNS records pointing to? And right now it would be like you could add a DNS record for Switzerland and Germany. However, like if something happens, you want to do a software update on the node, you want to, like it fails, Kubernetes is going to move Nginx into the other, one of the other nodes. But you need to update the DNS as well, and DNS is slow to update, and it comes with all these problems. Which means that you'll have to create some automation to track where every job is running, and then add the DNS record to point to the IP address where your server is running right now. And again, like with all the health checks, all of that, it's a complicated process. So there is an open source software right now. It's called MetalLB, and this is designed to run on Kubernetes. And what you have to do with that is that you connect every single server you have for your compute, where all your applications are running. You connect them to your routers with BGP. And Now, if I have like 100 servers in Switzerland and 2 routers, I have to set up 200 BGP sessions, luckily in an automated manner. And then all my servers can advertise prefixes to my routers. And this allows for dynamic routing, like the servers can participate in my routing through BGP. Now you then go and copy-paste some documentation, and the important thing is that you can change the IP addresses. So you find the free IP address that you have, and you give it to that service. So now you tell Kubernetes, whenever Nginx is running, go to that node and use BGP to attract this /32 or this /128 into this node. So now, whenever Nginx is running in a node, it's going to pull in that virtual IP that we just created for free. And if Nginx moves to another hardware node, that virtual IP is going to come with it. And right now, we've built a primitive that we can use. Basically, we have the IP addresses following the workloads wherever they run. So what can we build with that? The first one is that we can have cool DNS records like that, like all the big companies have. We can have them at home. You just apply this configuration file 4 times, and assuming you have the IPv4, you can have cool DNS records like that. But that's not the important thing. The important thing is that you can build easily architectures like Anycast. If you just go to Kubernetes, your control plane, and you tell it, I want you to run a single copy of Nginx in every server I have, or 1 copy per city or 1 copy per data center, suddenly your routers now have a route to that IP address, to that virtual IP address, directly next to them. So you can build basically a very simple CDN like that. If you have Nginx running and you add some caching of the requests, you can build an Anycast CDN, and the traffic comes from anywhere in the world. It gets into your network as soon as possible through BGP, like however soon is defined by BGP. And then you get to serve that traffic immediately at the edge. However, like not all applications are perfect, and a lot of times you're going to have to stateful applications where you cannot just spawn 1 million of these and then they handle the traffic and they play well with each other. For example, from the previous applications, the Minecraft server. If you have 10 servers, you cannot play with your friends now. If they're in the UK and you're in Switzerland, you're going to join different instances. They don't communicate with each other, and this is very bad. And there are multiple solutions here for that. The first one is if you do nothing, external traffic, it will get into your network as soon as possible, and then you'll have to carry it with your own backbone down to the source, down to where the application is running. So if we join this server here from London, I have to carry all the traffic from London, from an internet exchange, I mean, pick it up there, have it carried through my own backbone to the application, which is running in Zurich, and then I get the response back the same way. And this means that if I have my own backbone, I have the predictable latency that comes from this. I know the capacity of every link, and I can do some smart traffic engineering if one link is congested. Basically, I have full control of that traffic. The problem is that this is very expensive. I need to buy all those waves or those links, and this is not good for every kind of traffic. And this is where you can get lazy. If you run this application there, what you can tell to others is you can advertise this prefix only in Zurich, so only to the transit and peers in Zurich, which means that now even if I'm in the links here in London, I'm not going to tell you to send this traffic over to me. I'm going to tell you carry it to Zurich. I don't want to have to use my backbone for that. You find a way to bring it over there, and I'll open my door, I'll pick it up, and I will serve it for you. So that way you can use this for less important traffic, or when you don't want to, you cannot afford in some cases to use your own backbone. And this has problems because it goes through the public internet, right? So if there is some congestion because there's a Champions League match or something, you're going to have packet loss, or you're going to have conditions outside of your control. However, you have to accept that because the traffic is cheap. And if you have like, you can do groups like that. So if I have like 400 gigs between Zurich and Geneva, I can say, you know what, you can bring it to Geneva, it's fine. I'll still open my door and pick it up for you. So you can control, you can define these groups, and you can have others bring you the traffic into these groups. And you can now optimize how you receive traffic for that application. If I ever get, for example, a transatlantic cable to the US, I only want the most important traffic going through that, because that would be enormously expensive. And I only want to serve a few things from that cable, although I have it. I don't need to announce all of my prefixes everywhere. I can create like the European group and the American group, and then I can isolate all the traffic that I carry through that cable. And you can also create any kind of group, like regulatory groups. For example, if you have an application that needs to run in the European Union only, you can just remove the UK. That's a bad example maybe. But you can create all the kinds of groups you can imagine. And this depends on your actual capacity between links, on legal requirements, whatever it may be. You're in control of that. And basically just control your foreign policy, what you advertise to others, to bring the traffic through any path that you desire. Now, if you're just using Anycast, you need one prefix. Every application you expose, it gets an IP address from that prefix. You advertise it anywhere, and traffic comes as soon as possible onto your network, and the server is running there. You get the traffic out. That's great. And for the second use case, for important services where you want to carry this from your own backbone, you still can use the same prefix. It's a prefix you advertise everywhere. The traffic gets as soon as possible on your network, and then your routers know through your IGP how to carry it to where the application is running, and then you get the response back however you want. Now for the groups thing, you need one prefix per group. So if you have like 5 groups, like Europe and Switzerland and EU and all of that, you start to need one prefix for every one of them. And since the minimums are like /24 and /48, especially for IPv4, you need a lot of IPv4 to be able to do that. And you may say that this is expensive and all of that. Well, the answer to that has been there all along. Just offer a worse service on v4. You can offer this on v6, where you have unlimited prefixes. You can create as many groups as you want. You can have a very fine-grained policy. However, because most of your traffic will probably be v4, you need to keep that in mind, that whatever you do with them will not enjoy the benefits of this fine-tuned traffic engineering here. So a lot of CDNs are using DNS. Like, can we use that to help? Is it useful to somehow incorporate into that model? Assuming we have a DNS server we can automate. And what DNS can do in this model is that it can move a single domain into a different group. So if I want to create a CDN, I have every web server that can serve every website. I don't configure special groupings. And then, by changing the virtual IPs, I can move one domain name from the group Anycast to the group Europe, for example. And suddenly, as soon as DNS propagates, all the traffic is going to go to the European VIP. Someone can still talk to like a Brazilian web server and they would get a response, but DNS won't tell you to do that. So depending on how many groups you create, you can use DNS to change which group a website belongs to, either a subdomain or a domain, at any level you want. And obviously this happens at TTL seconds approximately, or however much some weird resolvers want. Like you have less control over DNS. And you now have two dimensions to work with on how you take your incoming traffic into your services. The first is BGP. You can change what a group means in less than a minute, and this is propagated globally. You just change where you advertise a prefix, you change your foreign policy, let's say, and suddenly traffic starts coming from another point of presence, from another transit provider. It's up to you to define this. And DNS can change between groups. For example, what I'm trying to do now is I can have all the domains belong in the important category as long as there's enough capacity in the network. So all the traffic I carry through my own backbone, but internally I have some priorities. And as soon as my links start getting full, then I immediately move through DNS some less important services into other more cost-effective groups. And this can happen in near real time. So if you have low TTLs, you can do that in a few minutes. And assuming your tools work well, and mine don't yet, but this is eventually you can create the right metrics by which you make these automated decisions. And of course, there are some things to be careful about, like RPKI. If you deaggregate your prefixes, if you do things like that, you may run into prefix limits, you may not have ROAs covering them, you may not have root objects. So you need to make sure that all of that works. And in case of automation, which was a problem I had, there is flap dampening. So if you just constantly advertise a route and then you withdraw it, you may get people to block this route for some period of time. So if your automation is too eager to move workloads between traffic classes, you're going to run into problems like that you have to be aware about, you have to design around. Now, we need to talk about ECMP. Basically, every router by default will probably only send traffic into one destination. So if you have 4 servers, only one of them, and they all advertise the same IP address, the router is going to pick only one of them to send the traffic to. And if you enable ECMP, then the router will distribute all the flows into these servers. So this you have to make sure this is on, otherwise you're not optimizing, you're not getting the most out of your compute that you deploy next to your network. The other important thing is that you need to have make sure that your router supports enough next hops. Like a lot of switches especially, they will say we can do ECMP but only up to 8 next hops. After that, it doesn't work. Like if you send me 10, I'll pick 8 at random and I'll use that. So you have to design your network. You have to look at your data sheets and figure out how much you can push it. And now that you're building trees, you have to know how to route those trees. If you have like a 48 port switch with 48 servers, and now you want a 49th one because there's too much traffic, if you add a new switch, suddenly one server is getting half the traffic and the other 48 servers are getting the other half of the traffic. So you have to keep all of these well-known, hopefully, things in mind of how to distribute that traffic evenly. Another thing to pay attention to is cascading failures and hotspots. So if you only have, let's imagine you have 2 routers, one is in Amsterdam, another one is in Athens. Obviously, you should expect that the Amsterdam one is getting like 90% of the traffic, and the Athens one is only getting 10% of the traffic. Like just because you have 2 routers, it doesn't mean you're receiving half the traffic in one data center and half in the other. And also, if the router fails, your traffic profile is now changing. So if you had like 100% of the Athens traffic being peering traffic, if your Amsterdam router goes down, now maybe 90% of your Athens traffic is transit. So you have to be able to plan for that when designing the network, when building the capacity, to work around all of these failures that could happen. For outgoing traffic, there's nothing special that is being done in this setup. Like, it's regular outgoing traffic. You can do whatever you want. If you want to do hot potato, if you want to carry it through your backbone, you can do that. And you also have the option based on the source IP address to direct the traffic however you want. So that's either the response to the original user query, or in general outgoing traffic you may have from your services, like they're uploading files to S3, for example, or whatever they are doing. You have to use existing methodologies basically to handle that. There's nothing special in this talk. So the whole model revolves around being able to use this simple primitive that the IP address follows my workload. I can define where the workload runs, and then I can have the network just handle the rest with simple automation or with just setting the prefixes statically. And that's all I had for now. You can contact me if you want anything, if you have any questions there, but I'm also obviously taking questions right now.
Any questions online? No? Okay, I've got a question. That's very interesting, first of all, so thanks very much. You mentioned that you had this kind of chain of events. So you can move your workload anywhere, and then the IPs move with the workload, and then the routing kind of follows the IPs. In Kubernetes, then, as you move your workload around, are you doing then some sort of health checks before the IP advertisement starts? So you're spinning up Nginx or whatever, doing some application checks, and then off the back of that, spinning up BGP? Or?
Yes, so you have the option to configure some kind of readiness check and some kind of health check. And you can say, I want to get a 200 if you make an HTTP request to that endpoint, or you can define some kind of simple logic there. And only then do you get BGP to advertise that prefix into that service. And when you do rolling updates, for example, the prefix is withdrawn, and then you update the service, then it passes all the readiness and the health checks, and only then do you start to draw traffic to that new service. So if you configure it on Kubernetes, then in all the life cycle of this application, this is being handled automatically.
Cool. Thanks. Any other questions in the room or online? No? Okay, then thank you very much, Antonio.
Great.